deliver regarding some of the system related to the process control. Okay, so I hope you can able to understand and it will give you some mileage of your research work. So we will quickly start our next session. This is the last session of our workshop. Okay, so Neelbrata, am I audible from your end?
Yeah, it is audible.
Okay. So
Are
we will
are the
start
sl-
the session.
are the slides visible?
Yes, it is visible. Yes.
Uh, is it moving?
It's moving. Please carry on.
Good evening, everyone. My name is Neelbrata Roy. I am here to present on the topic real-time application of Smith Predictor for systems with dead time in the presentation of 5 days virtual workshop, AI/ML based controller design and their application in real-time platform. I have done my PhD from IIST Shipur and presently serving as an assistant professor at RVS College of Engineering and Technology, Jamshedpur. The outline of the presentation is introduction, transfer function estimation, PID controller design used for CISO systems, Smith predictor for CISO systems, Smith dead time compensator for MIMO system, conclusion, future scope, and references. For designing any kind of controller, the first and the foremost important thing is to get the mathematical model of the system. So here I am discussing two types of systems, specifically the continuous stirred tank reactor and a heat exchanger system. There are many more systems whose mathematical models are already available in literature. So continuous stirred tank reactor, it is a common type of chemical reactor used in industrial processes. In CSTR, reactants are continuously stirred and continuously introduced and so that the composition of the products remains same. So this can be maintained by maintaining the inflow rate and the level or input output temperature or pressure. For this, let us uh, consider the relation of inflow and level. You can see equation number 1, the rate of change of volume of the tank, volume and the inflow rate is given by equation number 1. Here the time delay, is the uh, time taken by the fluid to move in the tank from the source. So taking the Laplace transform of that, we will get the value of relation as shown in equation number 2. Shown in equation number 2. Now consider the second model. That is the mathematical model of a heat exchanger. What is a heat exchanger? Heat exchanger is a device that is used to find the transfer function between two or more, that is used to transfer heat between two or more fluids without mixing them. So heat exchanger is basically used in many kind of process industries like heating, ventilation and air conditioning, that is HVAC systems, power plants and other. So here T out is the temperature of the hotter fluid and T in is the temperature of the cooler fluid, and tau d or the time delay. 1 minute again. Tau d is the or the time delay represents the time taken by the fluid to transfer from one part of heat exchanger to other part of it. So this is represented using a second order differential equation as shown in equation number 3. And the Laplace transform, by taking Laplace transform, we can see that the input output relations are having a time delay in the time delay term in time delay term. So this is one way to estimate the transfer function. But for this, we have to know the physical quantities. So to get rid of these things, what we do is we use relay based transfer function estimation. Now, in this relay-based transfer function estimation, we use a relay with a plant, and as we see in the figure number 3, and R is put to 0 in the for finding estimating the transfer function. First we say first we put R is equals to 0 and get the output Y, and the output Y. This output is known as the limit cycle output, uh, as shown in figure number 3, part B. From there, we first find the value of n dot, or n dot. We first find the value of n dot, and from here, that is given in equation number 5. And from there, we find the value of T1 and theta1, which are the important one of T1, theta1, and capital K, which are the main important elements of the transfer function, FOPDT transfer function, K by 1 plus T1s e to the power minus theta s. Like this, we can find the FOPDT. We can estimate any transfer function in FOPDT form. FOPDT form. But this plant can be a first order plant, can be a second order plant, can be any order plant. We can approximate that plant using this kind of transfer function. Now, if we don't want to use this method, there is one more method that is given by MATLAB, that is using the identification toolbox. What we do is we get the input output data of the plant, and using the input output data, we can just import the input output data in the toolbox, and the toolbox will give the transfer function by matching the input and output response. Using these methods, using these methods, we can find the transfer function of any uh, system which is unknown, model of any system which is unknown. Now, the next part is design of controllers. As you can see in figure number 5, figure number 5 is a very simple feedback control system having a controller C and a plant P. Uh, if we want to find the overall transfer function with the input disturbance of the plant D, the transfer function is given by equation number 8. But the main part here is to get the controller C. So there are methods to find the controller or design the controller are Ziegler-Nicholas based tuning of PID controller, IMC controller based IMC controller design and tuning, graphical method based design of PID controller, optimization based tuning of PID controller. In Ziegler-Nicholas based tuning of PID, in Ziegler-Nicholas, there are two methods to find the controller parameters using Ziegler-Nicholas method. The first is the process reaction curve method for an unknown plant. We use that, and the second method is to use direct substitution method. In this, we find the critical time period and the critical gain of the plant using Rao-Thurvey's criteria. Using this, we can find the controller parameters. The second method, IMC controller design and tuning, it is bit easy method. Here we need to know the plant model. If we just invert the plant model and filter on uh, cascade a filter of order greater or equal to the plant model of order of the plant, we will get the IMC controller, and we have to the field. If we tune the filter parameters, we can get the desired response. The third method is graphical method based design of PID controller. Graphical method based design of PID controller, we use either root locus or Bode plot method to design PID controller. The fourth method is optimization based tuning. The MATLAB toolbox has optimization based tuning. It uses Newton-Raphson method. There are other optimization based tuning methods like Gray-Wolf optimization tuning, genetic algorithm based optimization tuning, or and colony based optimization. There are lots of optimization methods. You can use any of them. What this method does is they generally mm, minimize a given cost function, and thus uh, minimizing this cost function like square error or integral time absolute error or integral of integral of uh, integral of absolute error. Either of the three cost function or all of the three cost function are minimized. On basis of that, the parameters of the controller are designed as the error function as this error function of the given simple feedback controller depends on the controller parameters. That's why on minimizing the error, we get the different kind of controller parameters. Now, there are some demerits of this simple controller tuning methods. That if the plant is having a delay within it, so the characteristic equation will also have a delay. So in case the characteristic equation have a delay, a delay is added to the phase is added to the system, and in adding phase, the system in case of adding phase, the system may become unstable. This happens when the delay is very high. Small delay doesn't affect this, but high amount of delay affect this. So for and third point is if we have if the plant is there are some modeling error in the plant. If there exist modeling errors, then what happens? The controller will not be able to control the uh, give the desired response. So to overcome this problem of having especially in point number 2, to overcome this kind of problem to have large delay in characteristic polynomial, what was designed is design of Smith predictor was designed. Now, this was Smith predictor was designed. This is a basic structure of a Smith predictor proposed by Professor O.J.M. Smith. Uh, Here GC is the controller, GM is the model of the plant, G e to the power ls, and e to the power minus ls is the model of the delay. So the input output relation, the or input output transfer function is given by equation of number 9. In case G is equals to GM and L is equals to LM, we can see that transfer in the equation number 9, there is no delay in the transfer function if G is equals to GM and L is equals to L. And thus we can see that GC into G to the power LS by 1 plus GC GM, there is no delay in the transfer function. In case there is no delay, we can say that the delay has been eradicated from the transfer function, which is one of the important property of a Smith predictor. If we want to design a Smith predictor, there should not be any delay in the denominator of the transfer function. First, secondly, the structure should be able to predict the output. In this structure, you can see that the second takeoff from the takeoff point GM e to the power ls, it is this part of the plant is able to predict the output of the plant output of the plant. So this is that's why this is called a predictor structure. And thirdly, ideal dynamic decomposition, that is this plant can be separated into two parts, that is a delay free part and delay part. That is shown in the figure number 6. The takeoff point is coming from the path between the delay free part and the delayed part. So there are these three properties. If any structure satisfies, it can be said that it is a Smith predictor structure. But this structure is having some problem. The proposed structure of Smith predictor. The problem is mm, this structure was only designed for stable FOPDT system. This was not valid for unstable FOPDT system. It has sensitivity to model uncertainties. That is, if the value of k changes to plus minus 20% of k, or the time constant changes to plus minus 20% of time constant, or maybe the delay changes to plus minus 20% of time delay, then then the given then the proposed system, previously shown system, doesn't give the desired output. Secondly, it has, if somehow noise enters in the system, the system will doesn't have the capability to reduce that. And thirdly, the most important, the disturbance rejection is very poor. If any kind of disturbance enter in the input side, the disturbance would directly get the output would directly get affected and become unstable. So for this, and many Smith predictor structures were proposed by many researchers. Uh, I have specifically considered a Smith predictor structure which was proposed by Tao Liu, which was valid for unstable system. This is the Smith predictor figure number 7. This is the Smith predictor structure proposed by Tao Liu. Here GC is the set point tracking controller. G e to the power ls is the main plant. GC1 is the disturbance estimator, whose work is to produce inverse disturbance, measure the disturbance D1, D2, and produce an inverse disturbance response so as to cancel the disturbance. GC2 is the stabilizing controller. GM and e to the power L minus LMS are the model of the plant and the time delay. This is the overall transfer function of the system, and you can again see that if G is equals to GM and L is equals to LM, the system will have no delay in the denominator of the transfer function. And as the system will have no delay in the denominator of the transfer function, we can again say this is a new Smith predictor structure. But this Smith predictor structure is only valid for unstable system. It is not valid for stable system. Secondly, if the disturbance rejection time is very high, and that is, it will reject the disturbance, but it takes much time to reject the disturbance. Thirdly, the tuning is model dependent. By model dependent, I mean to say that a particular uh, tuning method, the tuning method is particularly valid only for particular kind of models only. It is not valid for any kind of model. And fourthly, it is very sensitive to large perturbation in process parameter. That means if I vary the delay or vary the other parts of the other values of the transfer functions, the output will get highly affected. So to overcome this, we propose to change the tuning method. So if we change the tuning methods, we can see, and we change it using, if we change the tuning method using harmony search, using harmony search method, swarm optimization method, or ant colony method, or gray wolf optimization method, and compare it with the method of Liu, we see that on changing the tuning method, the disturbance rejection time becomes very high, very disturbance rejection becomes very fast, and the negative disturbance peak is also low compared to that of Liu. Thus, we can say that if we this is for the unstable plant, which was used by Liu et al. To prove in his work. So thus we can say that if we use optimization based tuning here, we get much better result than that of the uh, method proposed by Liu. Now, with this knowledge, we try to make this plant work for stable system also. In the work of Liu et al., the work proposed by Liu et al. Was only used for unstable system, but we have used the same controller structure for stable system. We can see the response that our plant rejects the disturbance very fast than that of Liu, but as disturbance enters in Liu et al.'s in the method proposed by Liu et al.'s, the controller becomes unstable, and hence we can say that our plant is that on tuning the control structure proposed by um, Liu et al. With Gray Wolf with optimization based tuning, we get better result than that of the previous. Thus, we can conclude here that tuning using optimization based technique is best suited. Secondly, unification of controller structure. We have unified the same controller for stable and unstable FOVT plant. Tuning method is model independent. That is, this tuning method is valid for any kind of model, whatever first, second, third, fourth, any order model. And also the disturbance rejection, you can see it here. The disturbance rejection is also very fast. So it can be valid seen from here. So next we will go to dead time compensator for MIMO system. Uh, the main characteristic of dead time compensators for are the first is dead time compensation. By dead time compensation, it means that removing the delay from the denominator of the characteristic equation. Output prediction, that is the system will give the output, and that is the model of the plant will give the predict the output. Thirdly, the ideal dynamic compensation. By ideal dynamic compensation, we mean to say the plant can be factored as a delay free plant, and the plant and the delayed part of the plant can be factored separately. It is to be noted here that for designing dead time compensator for MIMO system, all these three properties might not get satisfied. Either of the two property gets satisfied, we can say that it is a dead time compensator. Most of the dead time compensators have the first and the second property getting satisfied. Third property might not get satisfied many times. So the fourth property is uh, designer based on row and column translation. Okay. In this is generally applicable to those method. This was generally used with those type of MIMO plants which are non-square in nature. Previously it was used, now it is not used. This is this means non-square plants. That is, the input and output of the plants are input or output of the plants are different. That is, more number of inputs or less number of outputs, or less number of outputs, more number of inputs are there. For those kind of plant, previously this method was used, but after the after the controller switch dead time compensator design of Rao and Chidambaram, this method was obsoleted. The fifth method is to design a dead time compensator for MIMO system with and without decoupler. Generally, multi-input, multi-output system, the input outputs are coupled. So this makes the system very much complicated. The dynamics of the system gets very much complicated. By coupling, I mean to say the output of the system, the output, suppose it is a the suppose a plant is having two input, two output, and if the second output is also affected by the first input, this is known as coupling. So so generally many dead time compensator are also designed with a decoupler. But using decoupler, the problem is that the order of the system get increases. So these are the methods of the design, method and characteristics of for design of dead time compensator for MIMO system. Let us study the structure of dead time compensator for MIMO system. Uh, here GC, this is the dead time compensator proposed by Rao and Chidambaram in the year 2016. Uh, Here GC is the controller, GP is the main plant, GM is the model of the plant, GF is the filter, and GM is the delay free model of the plant. Now, if delay free model of the plant, that is, if Gp is equals to G11 e to the power theta s, theta 11 s, G22 e to the power theta 1 s, then Gm will be G1, G11, G22, G33 like this. It will have it. This model will not have any kind of delay within it. Now, in such a case, if we can see that the first two property get satisfied. That is dead time compensation and output prediction is there. But the third property, that is ideal dynamic compensation, is third property of dead time compensator is not satisfied in this plant. But as I have told previously that since if only two properties get satisfied for MIMO system, then the MIMO system can be said as a dead time compensator. Next, the the proposed method of Chidambaram and Rao has high disturbance rejection time. The disturbance rejection time of this is extremely high. And the third is that they have used arbitrary pole placement method, which is a hit and trial kind of method. And third and for fifthly, that they have validated this method for 20% plus minus 20% 20% of mm, model uncertainty. But if we go higher to that, then the system doesn't give desired response. So to overcome this, there is one more dead time compensator proposed by Digoli and Rico. This is more or less same as that of the Chidambaram and Rao method. Only changes that they have done is they have used linear matrix inequalities to design the controller and minimize the square error. Here also, only two properties of Smith predictor are being satisfied. The disturbance rejection is low as compared to Chidambaram and Rao. And thirdly, it is it can handle this design also has a problem that it can't handle uncertainty of plus minus 20%, and settling time of high disturbance settling time, that is the disturbance rejection. After disturbance rejection, the when the system again reaches the steady state, it takes lot of time. So to overcome this, we have proposed a dead time compensator. We have proposed a dead time compensator. Uh, Here, this dead time compensator GC. This is dead time. We have GC. Uh, uh, this is a dead time compensator proposed by us, where GC is the set point tracking controller. GP is the main plant. GM is the model of the plant with delay, and GMO is the model of the plant without delay. And Q is the disturbance estimator. Previously the all the plants which we have discussed or the controllers we have discussed doesn't have a disturbance estimator. We have used a disturbance estimator here. This disturbance estimator eliminates the disturbance very fast than that of the previous system, previous design systems. Now you can we have tuned the set compensator using swarm based optimization. Uh, Here also the two properties are being satisfied, that is dead time compensation and output prediction. That dead time compensation is being satisfied by we can, if we find the overall transfer function, dead time compensation gets satisfied, and output prediction, this part, the GMO part, will give the output prediction. So these two properties are being satisfied here. Thirdly, the disturbance rejection is very, fourth part is that disturbance rejection is very high compared to Rao and Chidambaram and Digo and Rico and Digoli. And the fifth is it can handle disturbances for more than 30%, or greater than 30%. Uh, Suppose we have considered this is a non-square example of a non-square plant. You can see the number of inputs. It is having three number of inputs. Generally, the rows are taken as inputs and the columns are taken as the outputs. The in such kind of plant, we have two output and three inputs. That is, that is the plant is a over actuated. So in the this is this plant is taken from a heavy, this is a example of a heavy oil fractionator plant, which is generally taken in the literature. It is an example of a stable FOPDT system, FOPDT plant. We can see that our output reaches the steady state much faster than that of the previously method. We have tuned using Gray Wolf optimization and TLBO method. These are the two outputs, Y1 and Y2, and these are the uh, outputs of the decoupler. Outputs of the, intermediate outputs. We can see that the intermediate outputs are nearly zero. That is the, we can say the system is decoupled from the, both the systems are decoupled. We are getting decoupled output. Although our output is having a slight overshoot, but it falls within the range. It reaches the steady state very fast. So we can say that our output is better than that of the previous one. Next, we can see that what we claim is the disturbance rejection. We can say that the system is having high disturbance rejection rate. The disturbance gets settled before than that of the method of uh, Rigoli and Rigo and Rao and Chidambaram. And although we have slight overshoot, but that doesn't matter at all. The disturbance get rejected very fast. Uh, and we can say that we can also see that the output at the that both the Y22 means both the couplings also get equal to 0. In the third part, what we have done is we have applied the disturbance, and we have there is uncertainty in the plant to plus minus 30%. And we can see that our proposed method reaches the steady state much faster and rejects the disturbance much faster than that of the previous one. And for the previous methods have high disturbance peaks. Thus, we can say that we can say that tuning using optimize that the tuning using optimization based technique is much better than that of the model based tuning, more other tuning methods. We have low fast disturbance rejection. The system is less sensitive to uncertainties, and also less control effort is there. The future scope is testing of advanced controller such as MPC and tube MPC, study the effect of sinusoidal and mixed disturbances. We have not only used step disturbance as the input. We have not tested on the system with sinusoidal and other mixed disturbances. Implementation of the scheme for higher order non-square plant. And thirdly is implementation of the proposed controller for unstable plants. These are the references. Thank you. Hello. Hello. Hello.
Hello, sir.
Hello. Hello.
Sir, I have one
Huh.
question.
Yes, yes,
Yeah.
please.
Sir, all these controllers are applicable for linear system only, right?
Yes, sir.
Okay. So what is the future of linear system in terms of research?
Sir, in
Is there
general, in yeah, in
yeah, yes.
process in yeah, in process control industries, still now we use linear type of controllers, linear systems are only used. As per the literature survey we have done, we have seen that linear systems are used.
Okay. Thank you, sir. Thank you.
So that's okay, but I have some small, okay, as related, it is related to Neelbrata's work. So linear
Mm.
system, okay, basically some idea also be there, like that if we are having a non-linear system, na, so for the implementation of the controller, so
Mm-hmm.
if we are not going for the linearization, so then
Mm.
the controller designing is maybe quite challenging, like IMC controller that here he has
Yeah.
uh, yes, he
Yeah.
has described about internal
Yeah.
model control. No? So if we are
Yeah.
applying all those controllers, so definitely we have to convert the non-linear system to the linear system and a LTI system. Then only we can go for the controller design for, and finally implementations. Am I
Yeah,
right?
yeah, yeah. It is. You are right. Actually, the I have recently a paper has been published by Professor Somnath Majhi and his group, where he has implemented this IMC controller to for a power for a power electronics, most probably a buck converter, most probably for a buck converter using this relay based estimation techniques. So they have used this relay-based estimation technique and estimated the buck converter using this FOPDT model. And for that, they have made the IMC-based controller and have got the desired results.
Yes, sir. Means at the end of the day, if you are given a non-linear system,
Yeah,
you have to linearize it and then design a controller.
yeah, yeah, yes.
So that is what I was asking. Means, thank you, sir. Thank you.
Thank
Okay, thank you. Any other queries? Is there any other query? Okay, so I hope there is no other queries from the participants end. So thank you, Neelbrata,
thank
for giving us your valuable time for
you.
the workshop as well as presenting your work to the participants. Okay, thank you.
Thank you.